Hello! In this video, we are going to prove the following lemma. 1 plus 0 is not equal to 0. Now, in this series, we are using a list of axioms for the complex numbers. These axioms come from MetaMath, and I'll leave that list of axioms in the description below. So let's remind ourselves what we're working with. We have a set, C, called the set of complex numbers. We're also given a subset of the complex numbers, R, which is called the set of real numbers. And we're given three elements of the complex numbers: 0, 1, and I. We're also given two binary operations on the complex numbers: addition and multiplication. So, given any two complex numbers, a and b, a plus b is a complex number, and a times b is a complex number. And also, we have a relation on the set of real numbers, the less than relation. So, given any two real numbers, a and b, it might be the case that a is less than b, and we write it like this. Otherwise, we say a is not less than b, we could write it like that. And from here, we have a list of axioms for the complex numbers. And here are some of the axioms that we're going to be using. We have axioms 3 through 9 and axiom 12. By the way, axioms 1 and 2 tell us the sum of any two real numbers is a real number, the product of any two real numbers is a real number. Now, axiom 3 is the commutative law for multiplication. So given any two complex numbers, a and b, a times b is equal to b times a. Axioms 4 and 5 are the associative laws for addition and multiplication. So given any three complex numbers, a, b, and c, these equalities hold. Axiom 6 is the distributive law. So given any three complex numbers, a, b, and c, this equality is true. Now, axiom 7 tells us that 0 is equal to I times I plus 1. So it relates these three constants together. Axiom 8 tells us 1 is not equal to 0. Axiom 9 tells us for every real number a times 1 is equal to a. And axiom 12 tells us for every complex number a, there is a pair of real numbers, x and y, such that a is equal to x plus iy. Right? So this is what we're going to be using. We're also going to be working with all of the results that we have proven so far. We have proven that 0 is a real number. We've proven that 1 is a real number. We've also proven the left cancellation law of addition for real numbers, which says the following. Given any three real numbers, a, b, and c, if c plus a is equal to c plus b, then a is equal to b. We've also proven that 0 plus 0 is equal to 0. And we have proven for every complex number a, 0 times a is equal to 0. In fact, since multiplication is commutative, we also have for every complex number a times 0 is equal to 0. So I'm going to include that as well. Now, before we get into proving that 1 plus 0 is not equal to 0, we're first going to prove a preliminary result, which is that for every complex number a times 1 is equal to a. Right? Axiom 9 tells us that this is only true for real numbers. Well, we can prove it's true for complex numbers as well. So we're going to prove that first. So, to prove our claim, let's give ourselves an arbitrary complex number a. From here, we want to show that a times 1 is equal to a. Now, since a is a complex number, well then by axiom 12, there exists a pair of real numbers, x and y, such that a is equal to x plus iy. So now let's multiply both sides of this equation by 1. So what we're doing here is, we're doing a times 1. Well, let's substitute a for x plus iy. So this is x plus iy times 1. Now, by the commutative law for multiplication, we could swap x plus iy and 1 around. And then, applying the distributive law, we can distribute 1 across the parentheses. So we get 1x plus 1 times iy. Now, applying the commutative law of multiplication here, 1 times x is just x times 1. And as for 1 times iy, we're going to apply the commutative law of multiplication here as well. So we flip 1 and iy. So this is just iy times 1. Now, by axiom 9, x times 1 is just equal to x. So that's just x. Now, as for iy times 1, well, we're going to apply the associative law of multiplication here. So we move the parentheses around y times 1. But then, we know by axiom 9, y times 1 is equal to y. So we're left with x plus iy. And x plus iy is equal to a. So this chain of equalities shows that a times 1 is equal to a. And that's it. This proves our claim. So, for every complex number a times 1 is equal to a. And because multiplication is commutative, we also have for every complex number a, 1 times a is equal to a. So we could flip this around. A times 1 equals a, 1 times a equals a, it doesn't matter. So now let's prove that 1 plus 0 is not equal to 0. So to prove that 1 plus 0 is not equal to 0, let's assume for a contradiction that 1 plus 0 is equal to 0. Well then, we are going to establish a long chain of equalities. What we could do is the following. We know that 0 plus 0 is equal to 0. Then, we also know any complex number times 0 gives us 0. So in particular, if we take the complex number ii times ii, multiply it by 0, we get 0. Well, since 0 is equal to 1 plus 0, let's substitute this 0 for 1 plus 0. Then, let's apply the distributive law. We'll distribute ii times ii across this parentheses. But then, we know that any complex number times 1 is that complex number. So when we do ii times 1, we get ii times ii. But then when we do any complex number times 0, we know that it gives us 0. So we're left with ii times ii plus 0. But then, by axiom 7, we know that 0 is ii plus 1. So then, let's apply the associative law of addition. We can move these parentheses around here. Now we know that any complex number times 1 gives us that complex number, so ii times 1 gives us ii. So we have this, but then in this parentheses, we factor out ii, right? So it's just the distributive law. But then we know that ii plus 1 is equal to 0 by axiom 7. So this is just ii times 0 plus 1. But we know any complex number times 0 gives us 0, so this is just 0 plus 1. So this chain of equalities shows that we have 0 plus 0 equal to 0 plus 1. But then, since 0 and 1 are real numbers, well then we can apply the left cancellation law of addition for real numbers. So that means we cancel out the zeros, we're left with 0 equals 1, or 1 equals 0. but this contradicts axiom 8, which tells us 1 is not equal to 0. Our assumption that 1 plus 0 is equal to 0 led us to a contradiction, so we must instead have that 1 plus 0 is not equal to 0. And so this completes the proof. And so yeah, that's pretty much it for this video.